What if the very fabric of our reality isn't what we thought it was? For over a century, physics has been built on two powerful ideas: Einstein's theory of general relativity and quantum mechanics. But here, as secret scientists don't often admit, these two theories are fundamentally at odds. They can't both be completely right. One describes the universe as smooth and predictable, the other describes it as chaotic and random. This conflict is the biggest challenge in all of science. For decades, the assumption has been that Einstein's theory of gravity would be the one to give way. But now, one physicist is proposing a radical new idea. What if we've had it backwards all along? What if it's quantum mechanics that needs to change? If he's right, it could overturn a century of physics and suggest that space-time itself, the very stage of our existence, is an illusion. The known two kings on one throne. To really get how deep this crisis runs, you have to appreciate just how powerful these two theories are. Einstein's theory of general relativity, from 1915, was a complete revolution. It tossed out Newton's old idea of gravity as some mysterious force pulling things from a distance. Instead, Einstein gave us a new vision. Gravity is the shape of the universe. Think of a bowling ball on a trampoline. It makes a dip, a curve in the fabric. If you roll a marble nearby, it follows that curve. It's not being pulled by a force. It's just following the straightest possible path on a bent surface. That's general relativity in a nutshell. Big things like planets and stars bend the four-dimensional fabric of space, and that curvature tells everything else how to move. It's a beautifully predictable picture. This theory perfectly describes everything from the orbit of Mercury to the way starlight bends around the sun, and even the ripples of gravitational waves, which we first detected in 2015. Then you have quantum mechanics, which runs the world of the unbelievably small. Unlike Einstein's smooth and orderly universe, the quantum world is a place of chaos and uncertainty. Particles don't have exact locations until we measure them. They exist in a superposition, a cloud of possibilities. The forces here work differently. They're not smooth fields, but come in discrete little packets called quanta. Quantum mechanics is maybe the most successful theory ever, underpinning everything from your smartphone to medical imaging. Most of the time, these two worlds don't bother each other. Relativity handles the very large, and quantum mechanics handles the very small. The problem starts when their territories overlap. The crack in the foundation. The universe has places where incredible gravity meets the quantum world, like inside a black hole or at the very moment of the Big Bang. In those extreme environments, you need both theories at the same time, and when you try to use them together, the math just falls apart into nonsense. The smooth fabric of Einstein's spacetime can't handle the jittery, random nature of the quantum world. Trying to combine them gives you infinities, which is a physicist's way of saying, we've got it wrong. For decades, the hunt for a theory of everything to fix this has been the holy grail of physics. Most attempts, like string theory and loop quantum gravity, start with one big assumption: that Einstein's theory of gravity is what's broken. The idea has been to break gravity down into hypothetical quantum particles called graviton, and force it to play by quantum rules. But after decades of work by thousands of brilliant scientists, these ideas haven't produced a single prediction we can actually test. It's a stalemate. But what if this whole approach is misguided? What if gravity is different from the other forces and isn't meant to be? This is where a radical new idea from Professor Jonathan Oppenheim at University College London comes in. His theory doesn't try to change gravity to fit quantum mechanics. It does the exact opposite. The new contender, a post-quantum revelation, Oppenheim's proposal, which he calls a post-quantum theory of classical gravity, flips a century of thinking on its head. He suggests that spacetime might be fundamentally classical, not quantum. In other words, the smooth, geometric world Einstein described is the real foundation, and quantum mechanics is what needs to be adapted to live with it. This is a huge shift. Instead of quantizing gravity, the theory keeps it classical but tweaks the rules of quantum mechanics. The result is a framework where classical spacetime can interact with the quantum world. But this marriage has a strange and fascinating price. The theory predicts the interaction must be stochastic, or fundamentally random. So, what does that mean? It means there's an inherent unpredictability in spacetime itself. This isn't the usual quantum uncertainty we're used to. It's a new, potentially more chaotic kind of randomness. According to Oppenheim's theory, this would cause tiny, random wobbles in the curvature of spacetime fluctuations that are bigger and more erratic than standard theories would predict. If this is right, it could be something we can actually measure. At incredibly precise scales, the very idea of weight would become unstable. An object's mass wouldn't just curve spacetime smoothly. It would cause it to jitter randomly. Imagine weighing an object on the world's most sensitive scale. According to this theory, you'd never get a perfectly steady number. The reading would jump around, not because of a flaw in the scale, but because the gravitational field itself is This opens the door for a real experiment to finally test whether spacetime is quantum or, as Oppenheim suggests, classical. This idea challenges the very foundation of modern physics. It suggests the path we've been on for nearly a century might be a dead end. And that reality is far stranger than we imagined. If your understanding of the universe is expanding right now, take a second to subscribe for more explorations into the frontiers of science. We're just getting to the most mind-bending part. Spacetime as an illusion. Oppenheim's work is part of a bigger shift happening in physics, where scientists are beginning to question whether spacetime is fundamental at all. Many new theories now propose that spacetime isn't the basic stage for reality, but is instead an emergent phenomenon. What does it mean for something to be emergent? Think about the temperature of a room. A single air molecule doesn't have a temperature. Temperature is a collective property that emerges from the average motion of countless molecules. Or, think about the screen you're watching this on. It shows a smooth picture, but if you look closer, it's made of individual pixels. The image is an emergent property of those pixels. In the same way, these new theories suggest spacetime itself might be like that image, an illusion created by a deeper, underlying reality. Our experience of a smooth, three-dimensional space and the forward march of time might just be a large-scale approximation of something far more complex and pixelated underneath. This idea is gaining traction because it offers new ways to solve some of the deepest puzzles in physics. For example, some physicists are exploring the idea that gravity isn't a fundamental force, but an entropic one emerging from the universe's tendency toward disorder. Much like temperature emerges from the motion of atoms, others propose that spacetime geometry is literally woven from the spooky entanglement connecting quantum particles across vast distances. In this view, the conflict between relativity and quantum mechanics might be a misunderstanding. We might be trying to mash together two descriptions of different levels of reality, like trying to reconcile the physics of a single water molecule with the behavior of an ocean wave. They aren't in conflict. One simply emerges from the other. The implications for our reality, if any of these theories prove to be right, if spacetime is a classical, fluctuating thing, or just an emergent illusion, the consequences would be staggering. It would force us to rethink almost everything we know about the cosmos. For starters, it could change our view of what happens inside a black hole. The singularity, the point of infinite density, where Einstein's theory breaks down, might not exist. A black hole could be a place where the fabric of spacetime simply dissolves, revealing the underlying quantum pixels of reality. This could also shed light on major puzzles in cosmology. Astronomers are currently scratching their heads over things like the Hubble tension, a big disagreement in measurements of how fast the universe is expanding. The James Webb Space Telescope has also spotted galaxies that seem too big to have formed so early in the universe. These strange observations could be hints that our theory of gravity in spacetime is incomplete. A new theory, like Oppenheim's, might offer an explanation. In fact, his team has even suggested that these random spacetime fluctuations could be an alternative explanation for the effects we currently attribute to dark matter. On a more speculative level, if spacetime isn't fundamental, could it be manipulated? If space and time emerge from something deeper, it opens the door to theoretically interacting with that deeper level. Ideas that have long been science fiction, like shortcuts through space or messing with the flow of time, might move one tiny step closer to scientific discussion. We're at a fascinating crossroads in the history of science. For 100 years, physics has been defined by the twin pillars of relativity and quantum mechanics, and haunted by the gap between them. The prevailing wisdom has always been that Einstein's beautiful picture of space would have to be broken down to fit into the quantum world. But bold new ideas are challenging that. Theories like Jonathan Oppenheim's post-quantum gravity and the broader concept of emergent spacetime suggest a different way forward. A path where spacetime isn't the fundamental bedrock of reality, but perhaps a grand illusion, where the familiar dimensions of space and the steady flow of time are just the large-scale effects of a deeper, stranger system. We aren't at the end of physics, but it feels like we might be at the end of the beginning. The cracks in our understanding aren't failures, they're signposts, pointing toward a reality more profound than we ever imagined. The next time you look up at the night sky, at that vast expanse of space, ask yourself, what if you're not seeing the foundation of reality, but just the surface of a much deeper ocean? What do you think this means for the future of physics? Is space-time fundamental, or is it an illusion? Share your thoughts in the comments below. And if you enjoyed this journey to the edge of what we know, be sure to share this video and subscribe for more content that challenges everything you thought was real.